All right, so hey everyone, and welcome to our mission number 4. This is the Kubernetes Masterclass. We are talking about, 12 missions, and we are preparing towards the Kubernetes Mastery as well as CKA and CKAD Bootcamp. And so far, we've talked about three things, starting with the week number 1, the mission number 1 being containerization, where we learned how to build container images. Podification was where we started with Kubernetes and started talking about how do we deploy pods with Kubernetes, troubleshoot those, and work with those as well. Mission number 3 was scalification, where we talked about replica sets, as well as horizontal pod autoscaler, that is HPA. That is the auto scaling feature of Kubernetes. This week, we're going to combine a couple of missions. We're going to talk about networkidization. So initially, this was meant mostly about service networking, but I'm going to take one more topic here and combine it with Ingress. So Ingress and Networkidize, so kind of becomes one mission now, mission number 4. So we'll go with 11 missions, 10 to 11 missions now. And what are we going to talk about this week is about how do we connect to our applications? How do services connect with each other? How does the underlying networking work? So we'll brief on all of these aspects. And we will be talking about service networking mainly, which is a very, very important topic. That's how the load balancing happens. That's how the service discovery happens. That's how you expose your applications to the outside world or start doing that. And that's how you connect one microservice to another in Kubernetes. From all of that point of view, service networking is very, very important here. We will also take up Ingress. Ingress is about, again, how do we add that layer on top of service networking and start routing our services to the outside world, is where Ingress controllers come in. Now, when you want to set up multiple microservices and set up a production environment, most likely, in addition to services, you will also need to know about Ingress controllers as well. Also, this does map to, how does it map to, let's say, the CKA and CKAD boot camps? Let me quickly bring up the curriculum there and talk about it as well. So this is the curriculum for the CKA and CKAD, and this is mapping to our missions and the sessions that we are doing here. And in addition to that, if you are a member, you already have access to the projects that we are doing weekly, and every mission has a bunch of projects so that you can practice and master that as well. And apart from that, you have access to the certifications, etc. So this week's mission, networkidization, is quite important because if you look at CKA curriculum, there are a bunch of topics, including how do we troubleshoot networking, a little bit of that, understanding of some host networking configuration, how does the pod to pod communication happen, all these type of services like cluster IP, node port, load balancer services, endpoints, DNS service discovery part, right? So how does that work? How do you choose a CNI plugin? A conceptual understanding of that. It maps to all of these CKA topics. In terms of CKAD, this is about how do we troubleshoot applications via services, and a little bit of debugging again revolves around pods as well as services a lot of times. So from that point of view, this topic is quite important. As well as Ingress, let's have a look at that as well. So Ingress wise, it may or may not have significance for CKAD and CKA. It does have. So how does it work? How do you add the rules and so on? So it does have some significance there. And despite that, in real world, ingresses matter a lot as well. Right. So that is the reason why we will take up these topics. And these two topics are very, very important. Let's get on with it. Are there any questions? Okay. Is there no sound? Are you able to hear me all right? Just checking.
Yes, we can hear.
All right. So from Zoom, perfectly fine. We are also streaming it to YouTube. I did a check before the session and it was all fine. And just wanted to check from the YouTube stream, is there an issue? You're able to hear me all right? Vivek says yes. All right. So maybe if you have an issue, maybe you want to check your volume. So just raise your volume because YouTube a lot of times mutes your volume. So just raise your volume on YouTube Live, and it should be all right. All right. Okay. So let's get on with our core topic here. How do we get started with service networking? And what do we have so far as a result of scalification is we have a bunch of pods. These were created with replica sets. We have autoscaler configuration as well. And we run some load tests, so it is there. And in addition to that, we have a service as well. So I do have a service created because I did that as part of this autoscaling last week. But nevertheless, we've really not looked into how services really work. Why do we need it? And how do we get started with all these configurations related to services? How do the spec related to services work? We will look into all of that. So let's start with, let's say we have a bunch of pods here. Right now I have two, but it could have been four, 500, doesn't matter. So I need to have a way to expose this application to the outside world. We're talking about the application, which is this. And this has 5 services in total.
We don't see your screen. Yeah.
Hmm, interesting. Okay. All right. Thank you so much. So we have 5 services in total, and let's say 1, 2, 3, 4, 5. Out of that, what do we have here? Um, what do we have here is a bunch of pods, right? And those bunch of pods are exposed with the services. And how does that work? And why do we need service in the first place? Let's understand these concepts first, right? So talking about this front-facing application, that is WOTAP, that's what we have deployed so far out of these 5. Now we want to have this is an external facing application. Users are going to connect to this application from outside of the cluster. So we need to have a way to expose this application to the outside world. How do we do that is where we bring in the service. Why do we bring in the services? Because we have the pods which have internal IPs. These IPs are not available from outside. Plus, these pod IPs keep on changing. Why? uh, the actual pod to IP mapping doesn't change, but it is the pods which are immutable. So we keep on deploying, redeploying, recreating the set of pods with every single change. That's what we do with containers in general. Since that happens, when we redeploy the pods, meaning we'll delete some of these and recreate it with the new set of pods, uh, the IP will change as well, right? With the new endpoints and so on. So we can't rely on these IP addresses which are in the constant or they're in flux basically, right? So what do we do is we set up some sort of a one single endpoint on top of that, which also acts as a load balancer. And not only that, we have a way, and this is where we create a service. And when we create a service, we have an option of choosing a type of service which can make it available from the outside world. Just like how we do port mapping with Docker, with hyphen capital P options, hyphen small p options, we can expose the service from the outside world in a similar fashion using a service called as a node port as well. So when we have to expose this outside, how do we do that? With the simplest way is using a service called as a node port. Now, how does that work? Is basically node port is equivalent of using port mapping in Docker, port mapping in Docker with hyphen capital P options, etc. And it works the similar way as in with port mapping, we take, let's say, we're running a container on one host. Let's say we're running it inside 80 port. We map some host port to it, like 8000. This is what we can connect to from the host. And from there, it gets mapped to the port 80. So in Docker, we use something like small p 8000 colon 80. or something on that line, basically, right? To make this port mapping work. Now, we have a similar situation, not exactly the same, similar, but not same. Why? Because now we have multiple nodes, not just one, and each of this node may have its own set of pods. And we are running multiple pods. So if you look at it, I have a pod running. Let's find out which nodes. Kubectl get pods minus o wide tells me one on worker 2, one on worker 3. So where are my pods running? I have my pods running on not this. It's running here and it's running here. It's running on port 80. Now, how do I expose it outside and give just one endpoint for the users? Is basically we create a service, and when we create a service of a special type called as a node port, that's what we're going to do here. What it will do is it will expose that just like port mapping, but across all the hosts. So I don't have to worry about which node my application pod is running on. And if the pod moves to another node, I don't have to bother too much, because when we use a node port of type of a service, it will do a port mapping, but across the cluster, as in on every single node, it will expose it on a specific port, or it will reserve the same port across the cluster. So when I say node port and define a port like 30,000, I can go to this node or this node or this node and access that pod on the same port, basically. That's the beauty about node port. So you don't have to worry about where my pod is running right now, and it just exposes it across the cluster. So when we create a service, and that's what you see here, you see a service definition, which has already been applied, and you have a service. So AKMS comes back again, the API version, kind, metadata, and spec. We expose it with a service, and the service whose type is node port. And with the node port, it will expose it on port number 30,000 on every single node in the cluster. Apart from node port, there are a couple more ports: port, target port, and the node port. What are these three different things here? So when you're running your application, where are we running it? Let's find out. We're running it in a pod. So whatever that application is listening on inside the container in a pod, so whatever the port it is running on, the actual application is listening on port 80, for example, or whatever, 8080 or whatever it is based on the application. So whatever you basically have as part of your image defined as an expose instruction as part of your image and the Docker file, which gets added as a metadata, that is typically your target port. Target port is the actual application port where your application is listening on that. That's your target port. Then we create a service. Service is like a load balancer. Think of it as a load balancer. Imagine it as a load balancer. When you create a load balancer, it has its own constant IP, and it will expose itself on, or it has a listener port somehow, right? So it has an IP and the listener port. That listener port on a load balancer, or equivalent of that in this case, is a port. That is your service port. And then when you expose it, or when you want to access the same service, so if you want to access that same service within the cluster, it will be service IP colon port. So when I create this service, and I actually have created already, but let me just apply nevertheless. So when I create the service, what happens is, you see it gets a cluster IP. A lot of times the tendency is to take this IP, to put it in the browser and try to access that service, thinking that it will work. It never does, because this is an inside IP. Cluster IP is within the cluster. The scope is the cluster. You can't access it from outside. Just like how your containers are, sitting inside some nodes. If you are on that node, you can access it using this cluster IP, for example. That could be possible, but not from outside, right? So how do we make it work from outside is where we use the node port. So node port is The port on the node, typically nodes are what we can connect to, and that is the node port which is exposed on every node, right? So I can go to any node and I can access it on port 30,000 and it does work. Since my nodes are containers only, I can just show you from here. So I have these 3 nodes or 4 nodes now, and I can go to any of these nodes and just do curl of this node. I need to be inside a container, one of the containers actually, or sorry, not necessarily 30,000 port is what I need to access. So 30,000 port, I can see it on any of these nodes, 0.5, even if the node is not running it, right? So this node, for example, is not even running that container. It's a control plane node, this first node. This application called as vote is not even running on that node. It's only running on worker 2 and worker 3, the ones you see in the green, right? It's not running on these nodes, but still you can access that application. This is just a HTML content. If you go to the actual node where this is a kind-based environment, so it's slightly tricky to understand. But if you access it on that kind environment on that node, 30,000 port, you see the same option. It's basically the same thing that you're seeing here. So whatever you see as options, and this is just a graphical interface, this is the HTML content, but essentially you're seeing the same. So any node that you can go to and access that port 30,000, you will see the application basically. That is the idea. And not only that, it is also doing the load balancing. I can show you that. I'm refreshing it every 3 seconds now. I just have a refresh plugin on my Chrome browser, and observe what happens in the bottom here, container ID. Every 3 seconds, when this is refreshed, it should typically show you a different IP address. Let me show you. Let me check why it's not. I'm going to scale the replica set, whose name is vote, with about 4 replicas. Yeah, so that I have more endpoints behind my service. I'm also going to check my service configuration. I will describe the service whose name is vote, and I see 4 endpoints. So these 3 plus 1 more, meaning now I should see whenever it refreshes, ideally, I should see a new pod ID displayed here approximately every 3 seconds. You see that approximately, right? Every 3 seconds, it shows up a new pod name. It's one of these 4 actually. So it's ending BR, this one. And now it is, again, come back to this. And then it's see this one now. And then now this one. And again to this. So approximately, if you look at it over a period of time, you're going to see it's doing a round robin kind of a load balancing. So when you create a service, what we essentially are looking at is when you create a service, you not only get a constant endpoint to connect to that application with, plus this service is acting as a load balancer already. And it's running on every node. You can access it on every node, right? That's how the services work. With node port, that's how it works. So you can go to any node, hit that port. If you, let's say, suppose you had 4 VMs, you could have gone to any of the VMs IP, and port 30,000 would show you the same application. It would do the load balancing, and all of that will automatically be in place, right? That's how the services work. So services give you constant endpoint in the form of cluster IP, and services give you the load balancing, which comes with it by default. Now, my question to you is, what is it that is running on every node, which could be responsible for this load balancing? Is there anything that comes to your mind? Any component, any specific component which might be doing the load balancing? Yep. Anyone? You can put it in the chat. You can speak up. Either way is fine. Kubeproxy. Yeah. It's not ProxyCube, but it's Kubeproxy, yes. Uh, but close enough. Either ways, right? So close enough that you can basically get access to basically Kubeproxy has a role to play, is what I would say here, right? Now, what is the actual load balancer? I'm going to show you, and you'll be surprised to see it. But Kubeproxy has a role to play. I'm going to bring up some details of that Kubeproxy to explain to you. Just give me one quick moment to do that. All right, good. So I'm going to tell you the story of kubeproxy. There is a kubeproxy running on every node first of all. But what role it plays right now, what role it used to play, we will talk about that. So when you look at pods in kube system namespace, that's the control plane namespace, you are going to see 3 instances, 4 instances in this case, because I have 4 nodes of kubeproxy running, meaning every node runs a kubeproxy. Now, is this the actual load balancer? That's the question. I'll go to one of the nodes, let's say control plane node, and show you where the actual load balancer is. Control plane node, because that is not even running the pod that we are referring to here, but it does the load balancing also. So interesting to know what's going on there. So if I go to this control plane node using Docker exec, right, and show you where the actual load balancing is, it would be fun to see. It is actually inside the kernel. It's not even kubeproxy. Kubeproxy does have a role to play, which I'll explain, but inside the kernel, and I'm looking at the IP tables, which is part of the kernel actually. And this is where the load balancing is happening actually. What you see is a lot of kind of a metrics like characters just flowing, but it has load balancing configuration there. I'm going to explain that to you, show it to you how it works. Before that though, let's understand the role of the kubeproxy then. If kubeproxy is not the load balancer, what role does it play? Let's talk about the story of kubeproxy with 3 diagrams here. Okay, this is the very first one. So kubeproxy in its earlier life, earlier avatar, was an actual user land proxy. When I say user land proxy, it's an application, basically layer 7 of OSI network layer stack we're talking about. So just like Nginx, such a proxy, it used to do an actual traffic control, load balancing. Everything was happening on kubeproxy, and kubeproxy had a very prominent role to play during that time. But there was a inefficient hop here, because when you look at the data, the actual request coming from the user, it lands up in the kernel anyways. IP table picks it up first, then it used to go to kubeproxy. From there, it used to go to, again, layer 4, then it would get delivered to the actual application. So there was this inefficient hop from layer 4 to 7 to layer 4 again. And that is the reason why they optimized it later with IP tables. So what you see right now is something similar to what this diagram is. So kubeproxy is literally sidelined. In its new avatar, the current life, kubeproxy is just sitting in the sites. What is the role it is playing? It is playing the role of updating the IP table rules. I'll show you. The actual load balancing is happening somewhere here. How do we find that out? We will look at the path of the packet which is entering our system. Like when we access this application, right? It is entering on our system somewhere through that port number 30,000. So if I go to one of these hosts and I'm on that master node or the control plane node already, and let's look at the path of that packet path that this packet takes, and we'll traverse it to understand how this load balancing is happening. So I look at this path. So IP tables, and I look at the packet which enters on port number 30,000 on this system. What happens to it is IP table has a bunch of chains here, rules and set of rules, and it points to some chains. So this is a rule which says, okay, if the packet enters with destination port being 30,000, send it to this particular chain. So if it is sending to that chain, we need to go here and find out what's going on now. So I will show you what happens to at this level. So I'm searching for it, and then I say, okay, give me 10 more lines, 10 lines further, right? And when I see that, there is something happening. All right, let's find out again. So this is port number 30,000. I pick up the chain here, and I'm trying to look up that particular chain, and about 10 lines afterwards. Okay, yeah, somewhere here. I think I need to figure out how many pods I have, and something to do with the way I'm running those pods. Okay, I just have two pods. Okay, okay. What is happening in my case is there is a horizontal pod autoscaler. So I scaled it to 4. It has gone back to 2. Why this is happening is because of our autoscaler called as HPA, which has a configuration of 2 being minimum, 10 being max. And since the CPU utilization, the traffic target policy is 50%, so it's much below that for an extended period of time. So it is just scaling things down to minimum. So either I can change this number, or in this case, I'm just going to delete the HPA so that it does not interfere with my replica set for now. Yeah, I'll just delete that configuration. And then I would scale the replicas count to 4. And now if I go back here, now you might have seen there's a rule here, some probability model and so on. And if you see 2 entries here, and now if I check again, you're gonna see 4 entries now. So 1, 2, 3, 4. So this has some correlation with pods, right? So because the number of pods match the number of entries here. You can see that already. The number of pods I have are 4. It matches that entry. I'll show you one more time. I'm going to switch the pods to 5, from 4 to 5. So I see 5 pods now. And as soon as I have 5 pods, every system, including this control plane node, would show me 5 lines here now. It updates. Now, how these IP tables are getting updated is where the role of kubeproxy comes in. So whenever you make some changes to the scale, for example, there is a kubeproxy sitting on that node, and the role of that kubeproxy is just to update the IP table rules. That's what this diagram explains. Earlier, everything was happening via kubeproxy. It is sidelined now, and it is responsible for updating IP table rules, and then the actual load balancing happens in IP tables. It is more efficient because the actual data path, the actual request coming from the client side are directly landing upon IP tables. IP table is doing the load balancing here. Those are the rules that you see here, and then it automatically directly goes to the pod, right, and communicates with the pod. Now, how is it doing load balancing? Let's have a look at that. It's a very interesting thing that IP table is doing. It is using the statistical mode random probability. So it's doing load balancing, a round robin load balancing at that using probability model. And you see the probability numbers for every line, there is different number. So there's 0.20, 0.25, 0.33, 0.50, and nothing here. So this is actually where the load balancing is happening. How do you figure this out is, let me explain this visually to you. So we are traversing the path of a packet which enters our system on port number 30,000. So when it enters on any system, and we're looking at control plane, but it can be any system, when it enters on that 30,000 port, it is trapped by the IP tables. IP table decides what to do with it next, and this is where our chain comes in. It is sending it to that chain. I've shown you that. And that chain has a certain number of entries matching the number of pods. So when I change from the replicas from 4 to 5, it changed the number of entries out there actually, right? And it started doing the load balancing, etc. And it is doing that with this probability numbers, 20.25, 0.33, 0.50, and so on and so forth, right? Now, what do these numbers mean? I'm just, for simplicity and explaining purpose, I'm converting into 20% in percentage numbers. And let's say we send 100 packets to the load balancer, to the service. What happens there is probability of the first line or first pod getting the packets is 20% or 0.20. So 20 packets go to the first pod out of 100. Now the question is, how many remain? So out of 120 went here, so 80 remain. Out of 80 now, 25%, that's why this number is different. Now 25% of 80 is 20, so 20 packet go to the next pod. How many remain is 60. Out of that, 0.33 or 33% of 60 is 20. To keep this number constant, the probability number is changing based on how many remain here. And then we have 40, so you can expect 50% of 40 to be 20, and then remaining packets go to the last pod. And that's what happens. So if you watch it for a longer period of time, you're going to see that distribution, round robin distribution. You actually see the number of packets right here. I'm sending this request every 3 seconds. It is refreshing somewhere every 3 seconds. It is refreshing. And because of that, yeah, here. So because of that, it is sending about 20 requests per minute. 3 seconds request. In a minute, 20 requests are going in. And because of that, you see, when I changed it, it was less number of requests. Because of that, you actually see, you see almost like not equal yet, but you see the number of packets, how they are being distributed. It will normalize over a period of time, and you're going to see like equal number of packets based on that probability number. So this is basically an implementation of, roughly an implementation of a round robin algorithm for load balancing. That's how things work. And that's how those are the technologies under the hood which are available right now. Now, IP tables is what we are using right now, right? It started with kubeproxy and just kubeproxy. Then came IP tables. Now, things are also evolving. So we, in addition to the IP table, even right now, we have an option to use a different mode or different driver for load balancing called as IPVS. IPVS stands for IP Virtual Server. Again, this is part of the Linux kernel, but this is actual load balancer. And this supports many different algorithms. So it has advantages over IP tables, as in it is high performant. It uses internally, it uses hash table based lookup, which are faster than the list lookup that IP table uses. So it's slightly faster, and it has another advantage that it supports different algorithms beyond round robin that IP table supports. Here you can have more implementation of different algorithms like least connections, destination hashing, and you can bring in other algorithm types for load balancing as well. That is possible with IPVS. So you can use IPVS, or when you set up the cluster, you can choose that driver as well. So that is an option that you have now, right? And that's the story of kubeproxy, how it evolved, how internal service networking evolved. And even if you don't know all of these things, that's absolutely fine. What you should know though is, how do we read the Kubernetes API spec and convert it into the YAML code, because that's where all these properties you will find. So even if you don't know the underlying implementation, if you can read the spec here, you can do almost everything with Kubernetes, because all of those properties will basically go in somewhere as part of some spec here. For example, if I look at the service spec, you have different properties. One of that property, I'll just show you one example. So one of that property is session affinity. I'll show you the example of this. But when, let's say, instead of IP table, when you start using IPVS, IPVS supports all these load balancing algorithms, but Kubernetes has not started implementing it yet. Last thing I know. But when it does, you will find a property here, like load balancer class or something on that line, right? Maybe policy or algorithm. And then you will have a choice between least connection, round robin, destination hashing, and those will be the actual values that you can define as part of that YAML, right? So I'm just showing you one example where I'll show you an example of session affinity. What is a session affinity? Right now, it is doing round robin, and that is the reason why you see every time it refreshes, it goes to a new pod. If you set the session affinity, it will not do that. It will bind you to a pod, one particular pod, and then it will always send you to that particular pod, basically, right? I'll show you an example of that. So I'll enable the session affinity. The values are these. These are the possible values. So you can set session affinity to uh, either client IP or none. By default, I'm using edit command to edit the service called as vote. And by default, you will see session affinity is part of the Kubernetes service spec. This is the service. I'm editing this object using kubectl edit command. So it brings it up from the cluster. That's why you see a lot more YAML. And it has a spec. So this is a service spec, as in properties of a service. And in here, you see session affinity set to none. That's the default value. I'll change it to client IP. As soon as I save this file, it will apply because I'm using an edit command. And when that happens, as soon as that happens, rather, you see I'm bound to one pod and only one pod. It's not going to any other pod. Until that pod is gone, it will always go to the same pod. That's what you see here right now. So this is how the properties work, and this is why you should be able to read the spec, be able to figure things out, because most of the questions that I get in Kubernetes session are the answers can be found here. So make this your reference point. This is the place where you go and seek answers, basically. Whether this property is available with the service or not. Can deployment do this? Can I add this particular property, or how can I add a particular property? The answers mostly are here. That's why I keep on emphasizing on the importance of reading the spec and being able to convert it into YAML. That is the most important part. If you can master that, you're already on your way to master Kubernetes, right? So I'm just gonna change this back to was it none? Session of, yeah, none it was. And since I've modified it back, now this should be going to a different pod altogether. So this is how things work in Kubernetes. This is how you should know about the definition of these properties and so on. Now, we talked about node port being a type of service. It is a type of service. If you read the spec, one of the type of the service, there are four types of services, okay? Cluster IP, which is default, node port, load balancer, and then there is an external name. Out of that, we are looking at node port. Node port is a quick way of exposing your application to the outside world, but it is not always the ideal way, okay? Node port is very useful for testing. Why it's not an ideal way is because it is range bound, as in you can only use a certain range of ports, which is not always suitable, mostly not suitable for production application, because you don't go to, let's say, amazon.com colon 32589. Yeah, you won't even remember that. You will always go to amazon.com. I'm just giving an example here, right? So you want to go to that exact domain name. That's why we created the domain names, so that we don't have to remember all these numbers in the form of IP addresses. So node port doesn't support that actually, because node port, if I try to make that happen, I'll have to make the service run on port 80. Will that work? Yeah. So right now it's 30,000 port. Let me try to edit, but I'll try to edit the service from here. All right. I'll try to change the node port to 80. Apply. It doesn't work. So it tells me that it is range bound. It tells me the range also 30,000 to 32767. Node port cannot work with any other port apart from that range. So I'll have to bring it back to 30,000. I can maybe use 30,200, 100, something like that between that range, but not beyond that, right? So how do I make it run on port 80, for example, or on a specific like default ports like 8080, 8000, whatever the port number, right? Beyond that range is where, or 443 for HTTPS, for example, right? So there are a couple of three options that we have here. Instead of using node port, you can use a load balancer. Now, interesting thing about load balancer is if you are on cloud, if you are deploying it with managed cloud and if you have the right authorizations, Kubernetes has the capability of calling the cloud APIs, creating the cloud load balancer. That would be a network load balancer, remember that. But it creates a load balancer, sets up all the listener configuration, everything, and has it all ready. So if you just set the type to node port, and if you're on cloud, you're going to see an actual load balancer created automatically on the cloud side within a few minutes. And that's the magic that Kubernetes does. Uh, However, since that is a network load balancer, you will not always prefer it, because one is network load balancer expensive. If you have multiple services, like 5 services to expose, we are talking about 5 different load balancers. You'll be paying for 5 times the money for the load balancer. Not always desirable, not always what you want. Sometimes it's advisable to have network load balancer for high performance, but otherwise you don't need it really, right? You can use external IP, which works with a small set of nodes and small set of services. If you have a startup with small set of services, number of services, you can use external IP as well, which will expose it on one particular node or 2 particular nodes or specific nodes, and it will work that way. Or you can use an ingress controller. Ingress is the most common option when it comes to exposing a service to the outside world and do the routing. Because with Ingress, even if you have 10 services, you just have one load balancer with Ingress, because Ingress does something called as traffic routing. It works like this. So in this case, if you look at this diagram, what you see on the right hand side are Kubernetes services like back office server, web server, API server. Think of those as Kubernetes services. On the left, you see the request coming in to or and landing up on only single place. So that's why it is a router. All the requests go to the same place, but with different headers like api.domain.com or domain.com/web, backoffice.domain.com, and it automatically gets routed to the correct uh, service. And that part is something we'll explore in some time. All right. This is the moment I'll take a quick break and take some questions. So I see some question on the Zoom, but if you want to unmute and speak, feel free to do that as well. And if there are any questions from, let's say, the live session on YouTube, I will take a moment so you can type in your questions. We'll pause and take a few of those. I already see a question from uh, in the Zoom session from Michelle. So the session affinity setting to client IP serves the same port to the same client IP. Is that the reason why it doesn't change? Yes. So basically, it maps it one client. It maps it to one particular pod. And once it has done that, it will continue to send this request from the same client to the same pod. I have humble request, do not send me direct messages on Zoom because I cannot handle it. And then I have to keep on switching back to everyone if I have to respond and so on. All right. So if there is a mic issue, I'll just be a little closer to it, actually. That's something I can do. I'll also reset my mic. Give me one moment. All right. I hope it is a little better. All right. Let's take some questions on the live channel. All right. So Vivek has a question. How does are handled if IP table is not in the system control plane node? So IP table is everywhere. IP table will be present on all the nodes, including the control plane nodes. So it is automatically handled at the kernel level, and it will automatically do the routing for you. So it will work on all the nodes. Kuproxy injects the chains. Ashfakar has already answered that question also. All right. Okay, Ashfakar has a question. I have a question about how does the DNS mapping handle it here. We'll talk about that. We'll talk about service discovery. That's our next topic. And Alexander has a question, if it is recorded session. Yes, so it is already getting recorded on Google, the YouTube. So it will all automatically be available on the same playlist on the same channel. So it will all, session is being recorded, meaning. All right. So I'm hoping that the mic and the audio is okay now.
Yeah, it's better.
Yes, also is okay.
Perfect. All right. So let's continue. And I'm going to answer that question about service discovery now. So service discovery wise, all right. Okay, do not send the private message. Again, I'll have to keep on switching back. So that's a request. All right. So let's talk about the service discovery. So a node port is just one option, one of the four options of exposing our application to the outside world. Remaining three being external IP, load balancer, or ingress controller, right? Now, all of this is valid for the front-facing applications. So when you look at these five services, we have vote, result, Redis, DB, worker. Out of that, the external facing application, as in the users, will interact with only the vote and result application, not with everything. Redis, DB, worker are just backend services. Databases, you definitely don't want to expose to the clients, of course. Same with Redis. A worker is just internal. It processes the votes from Redis, sends it to DB. It has no business talking to the outside world anyways, right? So in this scenario, when we have backing services, uh, what kind of service that we have to use here is none of the four that we talked about, right? Node port, load balancer, none of these four options. These are not service types, actually. None of these four options valid here. So here, if you have to expose, you have to just create a service with default type being cluster IP. If you look at this, the default type of service is cluster IP anyways. That's the default, right? Now, what is cluster IP service? Cluster IP service only exposes inside, as in it provides you a way to connect to your application using a domain name, right? That's where we are starting to talk about the DNS-based service discovery, the use of core DNS and all of that. Now, how does all of this work? Let me show you with an example. So we have this vote application deployed. Yeah. You see the front here. Great. But the moment I submit the vote, see what happens. It's trying to connect somewhere, trying to just load, and it ends up throwing a server error. Why this is happening, if you may have guessed already, is because this is just part of this microservices application stack. This is just front-end service, vote. The moment you submit the vote, it gets stored, or it needs to get stored in Redis. How does that communication work? is we go to the vote application, we go to the app.py. This is where the code is. How is it trying to connect to Redis? Is using a host name called as Redis here. See that? It's not using an IP address of Redis. It's trying to connect using a host name, a DNS. How will this work though? So there has to be some DNS server running in the cluster. And there is one actually. So we're talking about DNS based service discovery, which is a feature of Kubernetes already. And that is a result of, you see the pod running in the kube system namespace, these DNS servers, these serve it. And how does this pod, let's say this is a pod running a vote application. So I'm going to go to one of these pods, exec into this. So I'll get inside the pod, and then I'll try to use NS lookup of Redis. Can't resolve. This is the reason why this has failed, because it is not able to connect to Redis. It's not able to even resolve Redis. So there's no question of connecting, right? And this is the reason why it happens, because there is no service by name Redis available in this namespace. There is a service by name vote. So if I look up vote, it does resolve to the IP address of the vote. That is the cluster IP of the vote. As you can see from here. Yeah, you can see it's resolving to the cluster IP of the vote. This is what internal service discovery is, and this is what this cluster IP is being used for, to connect to that service from inside the cluster. So if there is another pod, another microservice wants to connect to it, it will resolve with vote if it is in the same namespace. If it is in a different namespace, it can use the fully qualified domain name, as in the FQDN vote dot instavote namespace dot svc dot cluster dot local, right? It can use this to connect to this service. Similarly, the vote application is trying to connect to Redis using a name. Doesn't work because there is no entry yet. That's what we'll have to create. All right. So I'll just explain how this works. So there is this DNS service running. So the vote application or this particular pod, I'm on this pod, and this is where I'm trying to resolve the Redis from. This is not working because there is no entry for Redis. There is no service for Redis, so that this entry is missing. The name Redis pointing to its cluster IP is just missing because it's not created yet. But the vote application can resolve the vote service because this is present. The service here is present. So in order for this to connect to this, we need to have a service created. As soon as the service is created, it will automatically make an entry to Redis, and every single pod is been configured to talk to this DNS server. You can see that in the etc resolve conf of every single pod. So I go to the pod, which is running vote, and I look up resolve.conf, and you can see 1096.0.10. 1096.0.10 is the DNS service. 1096.0.10. So it has been configured to talk to that core DNS server, and that's how it is able to resolve the services which are available. Is the Redis service available yet? No. So we'll have to create one. Let me create it here. So I go to KTS code projects and start dev. This is the path where we are doing everything from, and you'll see Redis service being available already. So Redis is a service where we create just a cluster IP type of service. We don't even define the type of service. Cluster IP is the default. So it uses that. And we just define the service port, which is mandatory, and the target port, which is also kind of essential. That is the actual pod port. And that's how it is going to connect to that. So let me create the service and show you. This is the Redis service, and it is now created. So if I am watching for ns lookup Redis, it should start resolving because I have a service by name Redis, which has a cluster IP ending 175. That's the IP you see it is resolving to. So it is now able to resolve. Sure. Let's see if it works. It does not yet. What is missing? We have the vote application. It is able to connect to Redis because Redis service is created. There is a DNS entry added. We see that resolving. You do see the Redis service. So what is it that is missing? There's a very specific thing. Anyone? Nobody noticed? Not the host entry. Host entry is not needed because we have a DNS server. So it is not host entry is not the answer. It's a very simple answer. We have Redis, sure, as a service. Let's describe it. Let me show you by describing the service whose name is vote. Okay. And now let me describe the service whose name is Redis. What's missing? Did you notice? Let's do this. Not the labels. Even if the labels are missing, it's not gonna affect here. Labels on the pods are there. Labels, even if are missing from service, it's still okay for now. But there is something else. Endpoints. That's the right answer. Endpoints are the pods. We created the service, sure. Where are the pods? If you don't have the application running, if you just have a load balancer, it's not gonna work, right? What we created service was just a networking configuration, not the actual application or the pods. So those are still missing, and we need to run those. And that's when I'm going to deploy Redis deployment here. Now, all of this is part of the lab guide, okay? So whatever I'm demonstrating to you, don't get worried about this. So it's already here. So this is part of the lab guide where you begin by creating a service. And I will share this on the chat. This is the lab guide for the service. And when you create it, you see this application. I showed you how this works, the load balancing and so on. How does it work under the hood? You can connect to the one of the nodes. In our case, the nodes are containers. So that's how Docker exec. And you can traverse the path. How does this work? Then you can find out the chain. Make sure when you grep for this, just pick this part, this much, and use that to grep so that you see this probability numbers, see the round robin algorithm, and then you can further look at the pod IP. It's pointing to the pod routes and so on. And then we have this internal service discovery that we're talking about. And I did this NS lookup part. Then I created the service. Then it started working, but it's still not pointing to anywhere because I don't have the endpoints. Endpoints are the pods, and the pods need to be created. And that's where I'm using Redis deployment. What is a deployment? We will talk about it in the next session, next week or a week after that. But that's what was missing here. And you see it created the deployment, meaning it should have launched the pods by now. So created replica set, created a couple of pods. Since the pods are coming up now, might have already come up. They're running. I have a couple of endpoints for Redis. And now if I describe the service called as Redis, I do see the endpoints. Since the endpoints are there, it should work now. And this is the internal service discovery. Vote is connecting via DNS to Redis, and there is no IP address business. And this is very useful because then the same code, you can take it and run it in your cluster. Whatever the IP address of the Redis in your cluster is, it doesn't matter. because we have the name-based discovery. So it makes it very easy for us to connect or interconnect these microservices without bothering about all this underlying configuration, right? It's automatically taken care of. Another important thing here is the endpoints. You can also list the endpoints separately using get EP or endpoints. How do these endpoints are collected? How does service know which endpoints are available, whether they are available or not? Is again, this goes back to the metadata with labels and selectors. So it is very, very important that you have the right selectors. I'll show you. So if I edit the service called as vote, I will watch for the endpoints, okay? What you see the endpoints are dynamically collected, changed, and all that. So if I edit the service and if I'm selecting, the selector is similar to replica set selector we talked about. It's just a simpler label selector. So if I'm selecting for the label which doesn't even exist, what are we selecting? We are always selecting the pod based on the pod labels, right? We are talking about pod labels. So out of these, it's going to select the pods whose label is this. This doesn't exist now. Since that doesn't exist and apply the change, you see the endpoints are gone. So vote is not pointing anything anywhere. If I refresh, it should be gone, right? So selectors, very important thing to understand. And if you, let's say you have the selector, but it is wrong as in it is pointing to a different application that is even worse. Now this part is easy to understand. So you don't have the selectors at all, or no pods exist with that. But if I, let's say, use a selector called as role is equal to Redis. Now I have the endpoints, but it still doesn't work because what I'm selecting, the set of pods I'm selecting are not even running my web application. It's running Redis. So it will never work. I may route traffic to a completely wrong application unintentionally. That is something you need to be very, very careful about. So you must ensure that your selectors are written correctly and it matches exactly the application that you want or desire it to send the traffic to, because your endpoints are going to be collected based on the selectors. And your application will get exposed only based on that. So that part is very important to understand. Any questions? Okay, this is about service discovery. So most of the applications that you don't want to expose to the outside world, you are going to use only cluster IP service, like Vote, Redis, not Vote. Vote is external. So here you have to think about node port, load balancer, external IP, or Ingress. For Redis DB, you need to use cluster IP. Worker in this case doesn't even need a service. What would be the situation when you do not need a service, or you may not need a service? So do you create a service for everything, especially with replica sets, the application like this worker? Worker doesn't need a service because it's like I have a phone, but I don't have to publish my number if nobody is going to call me, right? So worker, nobody's calling. Worker is calling everyone. Worker connects to Redis, worker connects to DB. It collects the vote from here, processes it, submits it somewhere else. So there are no incoming connection to worker. Since nobody is trying to connect to worker, nobody is trying to discover worker. It is okay to create a service, but it is just redundant. It's not necessary. So worker in this case would not need a service. This is based on the application. So if you look at the arrow, it may not, you may not be able to figure this out. But these are the situations when you do not need a service actually. So Redis DB both need service because you have vote connecting to Redis, worker connecting to Redis and DB, result connecting to DB. I'll show you the worker code actually so that you get an idea. So there are no incoming connections from anywhere else. But if you go to workers code, you do have this Java application which is connecting to DB, yeah, and Redis. So you see, it's initiating those connections through this block 11 and 12. And it's using the names again, DB and Redis. Service discovery is happening with the name-based service discovery. That is the feature of Kubernetes. That's why you have the core DNS. And that is how it works. You just have to create a service and it creates a IP address. It creates a domain name if you have this DNS service available for in the cluster. And mostly you will see that add-on. Okay, that's how the services work. We talked about how do we expose the service outside. We talked about how services find the pods using selector. That is very important. You may have some troubleshooting exercise related to that, even in the exam. So this is very important to understand this concept. And then service gets a cluster IP. You can disable that. If you disable the cluster IP, it will point to the pod IPs directly. So it will show the pod IPs instead of the cluster IP. That service would be called as headless service because you remove the head, it directly points to the pod. Sometimes that is useful, but otherwise services get cluster IP by default, and you have a DNS associated with that service as well. And if you have, let's say, DNS servers within the cluster. Those are some of the key concepts related to services. There are a few more, but these are the key concepts related to services. Any questions so far here? Rujain has a question. So deployment label is matched with service selector so that about template label, container label. So services don't care who created the pods. It is just the pod labels. Everyone tries to match. Services are acting independent of deployment or stateful set, or maybe it would have been created by daemon set, stateful sets, deployment, just replica set in this case. There's not even deployment in our case for what application. So as far as services are concerned, what is it selecting? It's just set of pods. Replica sets, again, a set of pods. So there is no direct connection between or communication between deployment and a service. It all happens via the set of pods. So replica sets are maintaining a specific set of pods with certain labels, and it has a capability of launching, scaling, removing, and so on. And services, whichever pods with particular selector are available, it just routes traffic to those. So that's how it works. So it's very decoupled kind of architecture that it has. Okay, so headless service, I'll explain a bit. In on-premise cluster, sometimes service discovery does not work, how to troubleshoot. So you will have to look up how do you troubleshoot is you go to one of the pods, whether it's really working or not, right? In case of Kubernetes, it's quite reliable in my experience. This used to be a problem with Docker Swarm because the way services would propagate would take time, and sometimes it will be delayed, and there were stagnant configurations and all that. But with Kubernetes, mostly it works fine. But how do you troubleshoot if you have to is you begin by getting into a pod and try to do something like NS lookup. So there are a couple of tools related to uh, name server debugging, right? NS lookup is one, dig is another. So you can look up. One is check the configuration, whether this is fine, you're able to connect, or the right name server, which is the DNS server, is configured or not. You can do NS lookup of a particular service, check whether that is available or not. If that is not available, you check whether the service is created or not. Sometimes you may have a service, maybe there's a network policy issue, something like that. So there could be multiple issues, but general pointers I can give you is check whether the service exists, check whether the endpoints are there, check whether you're able to do run NS lookup. So that's, or dig is another alternative tool there. And go to one of the pod or create a new pod, try to access the service from the same namespace typically. So there are all these issues. A lot of these issues are just because of misconfiguration and misunderstanding of service networking. So if you understand this diagram well, you pretty much understand service networking quite well, right? Now, talking about headless service, and there is one more service type actually. I'll explain that too. So if you look at the type of services, we have cluster IP, the default one, node port, exposes on every node, range bound 30,000 to 32768. Load balancer works on cloud, only on cloud. Node port works everywhere, okay? Load balancer works only on cloud. Non-cloud, non-managed environment, load balancer doesn't work anyways. Cluster IP, node port you have available. Apart from that, there is external name. If you look at this diagram, you may get confused that, oh, external IP is a type of service. No, it's external IP is different than external name is. External IP is just a service property. It's one of the specs in a property where you can define an IP address of your existing physical load balancer or IP addresses of some of the nodes, and it works with that external IP, that is, right? External name, on the other hand, is a type of a service, typically a headless service. And the way it works is, and the situation in which this is useful is, I have to explain this visually. Let's say you have an environment where staging and production, right? In staging, this is your staging, this is your production namespace or environment. In staging, your database is running in a pod. So you have a pod, set of pods, you have a service called as DB, and your application connects to DB, which goes to the pod. Works fine with the default. Now imagine in production, your database is not running within the cluster, but it is running as an external service, like an external hosted database somewhere. Like on AWS, we have this relational database service, RDS, or managed databases on cloud, where you get a CNAME entry or maybe set of endpoints or actual IP address or CNAME entries. So you're supposed to use the CNAME like a domain name. So what you do is you create a service still by name DB and use external name as a type of service, and point DB, create an alias to that, pointing to this basically. So when the application connects, so the good thing about this is your application does not need to change. So I just showed you the application code. It says host is equal to DB. So that works here, connects to the pods. That works here, connects to the external service, external name. So this serves as an alias. And due to this, you don't have to change the application code, which is a good thing. So it can be a CNAME, which is a domain name entry, or could be a set of IP addresses, which could be endpoints. In either case, you may want to create a headless service without cluster IP, not just selectors, but service without cluster IP actually. So that's more like a headless service that you create, right? That's an example of headless service. Sometimes you want to send the traffic to the pods with pod IPs and not have a service IP internally, right? Some applications need you to connect using a IP address, or you need to know about that and so on. So in such scenarios, you may want to use a headless service. Headless service is one without cluster IP, actually. Okay. Okay, so Rojan has a question about this happens in K3s. So K3s, we'll have to look at that and figure out what happens in K3s, how has it been set up, so that we can specifically uh, answer that. I think the question is from the DNS point of view. So check if DNS server is running or not. That's the first troubleshooting step that we'll have to start with. What used to happen earlier, okay? Earlier, what used to happen was DNS servers was not shipped with Kubernetes. So there used to be an external DNS service you had to deploy additionally. So maybe with K3s, default DNS server is not being set up or was not being set up, and you had to deploy it separately. So that may be the step which is missing. So check if you have the core DNS server running. Earlier, there used to be an application called as SkyDNS. Then Kubernetes team created their own DNS server as well. And that is what you typically see as the core DNS being part of the core Kubernetes environment. And check if that is present or not. If that is not present, your DNS discovery will not work anyways. All right. So the next question is about Ingress controller. So Ingress controller, we'll talk about that, right? So if the core DNS was there, so we'll have to figure this out, Rajan. So generally, these kind of questions we can take up in our group coaching sessions on Thursdays. If you're a member, you can join and bring these questions in, have an environment. We can also uh, troubleshoot these kind of issues live, and that becomes a learning for everyone else as well. So do consider being a member. By the way, if you want to be the Geek member, where you can get access to all the courses, projects, we have a library of projects that we're creating, which can not only help you master Kubernetes, but also prepare for CKA, CKAD. We're trying to do group coaching, group project. We have like coaching sessions where we've started doing a lot of interesting stuff now, and it's been very interactive recently. And we discuss things, discuss projects, come up with the solutions, present those solutions, have people present solutions, right, and all that. And our members are participating, so that's very useful. And we also have the certifications as part of it. So it's very affordable pricing, and I've created a coupon code in for the first 10 members, only for the first 10 members who really want to go ahead and take this membership up. So which gives you access to the courses on Kubernetes, Docker, and everything that I just mentioned. And you can get it at an amazing deal. It's there on the live stream. It is only for the first 10, you know, first 10 people who enroll into this session or this membership program, right? And then you also get to be on the Zoom call and ask questions from there as well, right? And then our coaching calls generally happen on the Zooms, right? So that's about the membership in case if you are interested, and it can add a lot of value. You'll end up taking action, being, doing stuff, following the structured courses, and doing the projects as well, which could be interesting for you. Okay, talking about Ingress controller now. That's going to be our last part of the session anyways. So what is an Ingress controller? I did mention to you that you have external IP, node port, and load balancer. On one side, you have Ingress on the other side. Why? Because all of these are layer 4 services, the external IP, node port, load balancer. Layer 4, as in we are talking about the OSI networking model, and theoretical model, right? And then we implement it with TCP typically. But it's at the transport and network layer, this TCP IP thing. And the layer 4 load balancer typically is a transport layer. Versus layer 7, Ingress is at the application layer. Since it is an application layer, it is an actual application like Nginx is. And you can use the Nginx modified version of that as an Ingress controller as well. So it is an actual application. It has a lot more intelligence to it. It can do a lot more interesting things like, one is this routing that I talked about earlier. Just give me one moment. Yeah, this kind of a routing. So you can send the request as api.domain.com, it sends it to the right service. Domain.com/web will send it to the right another service. Backoffice.domain.com will send it to another service, right? So based on your headers, it will automatically route you to the relevant Kubernetes service. Plus, it can do many things. For example, it can also do like TLS handling, your TLS certificate configuration. It can do traffic shifting, like you can have a canary release or blue-green deployments, and let's say 80% is going to this service, 20% is going to the backing service. You can do all this kind of interesting stuff with Ingress controllers. You can also do, let's say, load balancing. You can bring different types of load balancing algorithms, because Ingress controllers not necessarily uh, are sitting on top of a service, as in it is not routing to the service, but it basically gets the endpoints from the service, and Ingress controllers talk to the pods directly. Since they talk to the pod directly, you can choose a different algorithm for load balancing than just a round robin or the default. and so on, right? So Ingress, you can do a lot many interesting things. And Ingress is typically how, in a larger environment for sure, you will expose your application to the outside world with your domain names and stuff like that. And on clouds like AWS, you can use application load balancer. On Azure, you have application gateway. On GCP, you have a similar thing, like there's an application gateway or load balancer, one of the names, but it essentially you have some sort of a cloud load balancer, layer 7 load balancer, like application load balancers or gateways, and those can act as ingress controllers as well. If not, on-premise, you can set up anything like Nginx, Traffic, Ambassador, HAProxy as an ingress controller. There are ingress controller versions of it available, not a classic vanilla Nginx you can take and set it as an ingress controller right away. You have to use a ingress version of it. Now, what is an ingress version of Nginx mean, right? Or something similar to that, like Traffic mean. So let me explain that concept here. So what that would mean is basically ingress controller is sitting inside your cluster, and it is a wrapper on top of Nginx, for example. And that wrapper is constantly watching for something called as ingress rules that you as user will create, right? And then it will talk to. So as a user, you will create some sort of an ingress rule. Ingress rule is nothing but a mapping. Like this diagram shows you when you send the traffic as some header, right? So when you say api.domain.com, it should go to API service. Who lets the ingress know about it? So that would be user, like developer, like us. So when you deploy your application, you will add an ingress rule. In your ingress rule, you'll say, okay, if the header has vote.example.com, send it to the vote service on port number 80, meaning the endpoints received from the vote service, send them on port number 80, basically. That's what it would do. So we're just defining this mapping, and every application, every service will have that kind of a mapping. So as a user, when you submit that rule, the good thing about this is typically, if you look at the way things work in an organization is, oh, as a user, as a developer, I'll deploy my service, or I may do that. And then on top of that, I'll have to raise a ticket with a DevOps person or a ops person or someone from the network team. And they would go and update the rules related to Nginx or something similar. Because as a developer, I don't have the control to Nginx server and its configurations. So that is mitigated here because this is like a bot. Ingress controller is just a bot sitting on top of your actual application, and it is listening to the ingress rules that the developers will provide. And as soon as the rule is created, the ingress controller will take an action and update its own configuration. So Nginx ingress controller will update Nginx configurations. So it's like a bot sitting there watching for some configurations, and as soon as it receives some, it takes an action based on that. That's how the ingress controllers work. And as soon as that happens, it starts routing the traffic, and then you can start using it and looking at it as well. So the ingress controller that I am going to demonstrate, and I'll share this link with you, the lab guide, basically. So this lab guide is the latest one for Ingress. I'm sharing it in the chat. I have a couple of two different places to do so. So give me a few seconds. Okay, here goes the Ingress lab guide. So what do I need to do is you need to deploy a hem as a tool first before you get started anyways, right? If you don't have that. Yeah, I have it, so I'll just proceed with it, set up part and all that. So when I deploy Ingress controller, it will launch the actual Ingress server, the traffic Ingress server in this example, and it will start listening for the Ingress request and all that, or request with certain domain names and so on. So why do I use traffic? Why not Nginx and others, right? Nginx is a very popular one. The reason I choose traffic is, one is it is not only lightweight and fast, but also the most important being it comes with a management UI. So it is very easy to get that feedback because a lot of times we get stuck with certain things, right? And it's always better to have a visual interface like this, for example, to see what's going on with my deployment, right? It's easy to figure things out. It's easy to understand, learn, and then debug as well. So same thing with Ingress, especially with Ingress, it's quite tricky if you are a beginner. So it is always good to have a UI which can help you and give you that visual feedback interface, help you troubleshoot if something is wrong. And that's the reason I prefer using Traffic for my trainings. But in the project, you will have to deploy Ingress with Nginx, and there'll be some advanced projects that I'm going to put as part of our Kubernetes bootcamp for the members. Right. So how do we deploy this? How does this work? I'm going to show a demonstration now. I'll deploy Ingress as a traffic as an Ingress using hem. We will spend some time with hem later. So if you just follow the instructions here, it's going to deploy it using a package for traffic. It creates a namespace for itself as well. So I'm going to use get all, the namespace called as traffic, and keep watching that because it will show up something in a few minutes. To provide some properties for configuring this traffic. Generally, I take this topic after teaching hem, but since we want to cover it together, and it does make sense to do so, I'm gonna just go ahead and skip over to the installation part. So let's assume that traffic is deployed, right? And you can see that in the namespace below, that it has created its own pod, a service, its own deployment. It's running on certain port as well that you can see already. I shall see traffic running on port number 30,400, where it will actually receive the actual traffic with something like api.domain.com and this domain.com/web and so on. So in my case, it's 30,400, 300, 400, and 30,300 would be my dashboard. So I have to go to what is the same IP where everything else is running. 30,400. So it says for page not found. That is expected because now it is expecting me to send the traffic with some domain name. 30,300 on the other hand, I have to use 30,300/dashboard. Now, remember, this is not going to work either. You have to use dashboard slash. That trailing slash, very, very important. From the experience I'm talking, because I spent like 2 hours just to figure out why it's not working. And then I just realized that, oh, I was making a request as dashboard and forgetting about the trailing slash. Very important. Remember that. And this is the reason why we use traffic, because you see everything graphically. You can see what routes are there. And let's say kubeops views there. So we'll have vote.example.com shortly. And you see the load balancers on the back end. Like this one shows me, oh, what is my route? What is my backing service? What is the actual pod endpoint? What kind of load balancer is this? Whether it has any specific configurations. So you can troubleshoot from here, right from when you create an ingress rule, whether it shows up or not. Because unless you see it here, it will not work anyways, right? So it is helpful to get that feedback. It's helpful to see it, how it has been configured. and it is easy to debug this way. So if I try to access it as vote.example.com, whatever, uh, anyways, it's not going to work, right? So if I try to access it right now, it's not going to work because I do not have the rule created for that. So I need to create one. How do I do that is where I am going to add a rule which is given here. This is what I'm talking about now, this ingress rule that as a developer, I would write, and that just says it's an ingress rule called as vote.example.com. So what I'm saying is, okay, look at this path. If the header has vote.example.com rather, send it to the service by name vote port 80 in the namespace called as instavote. That namespace also important. And I am going to yeah, copy this over. Okay. And as soon as I create the rule, I will show you. There is a rule for maybe all the namespaces. There is a rule for kubeview. Kubeview is nothing but this visualizer, right? So I can, if I have a name for a domain name created with it, it may work as well, right? And then I create vote-ing. You see, it just created this rule. If I describe it, it shows me that it will point to this service which has picked up this endpoint. So from service, it picks up the endpoints. You can also see this visually here, right? So with traffic, this is why it is useful, because now I can see the rule vote.example.com, which is pointing to the service whose name is vote on port 80, and it has picked up these endpoints 1, 2, 3, 4, 5. Again, if I scale this down to 3, this will change in a few seconds. If not, I'll just refresh it anyways. Should change. So you can see that it's giving me that visual feedback that whatever changes I'm making, like I've just removed some replicas. So service would have updated the list of endpoints, and that's what Ingress is looking up, and it automatically updates its own configuration. If you have Nginx, it would have updated the Nginx configurations and whatnot. Now, what do I need to do is send the traffic with the name, domain names, vote.example.com or equivalent of that, whatever the name here is, right? Or whatever the name here is. How do I do that now is where I have to add some domain name entries somewhere, right? Or at least override some configuration, because now I have to send the traffic to the same ingress, wherever the ingress is, which is this IP, right? But as a host name. So I need a domain name server, or I don't own vote.example.com. So I can't update it the domain name server. But what I can do definitely is locally, wherever my browser is, that is my Mac or your desktop, your workstation, not a server where your Kubernetes environment is. This change will happen on your Windows or your Mac, or wherever your workstation is, wherever this browser is running from, right? So I have to go there and update the configuration where I can override saying that, okay, this IP is my vote.example.com. So if you send traffic as vote.example.com, translate it into this IP. That is the host file entry. Someone had mentioned it earlier, but we are changing it now. So I'm going to my Mac and changing the hosts file entry right here. So this is the host file entry. So I'm actually pointing everything to the same IP. So basically we're routing. So we're sending it to the same address. It will automatically route. The ingress will do that to the right service. So now if I say vote.example.com instead of IP, will not do anything, right? So IP 30,000. 400. 30,000 is the node port, which is still working. 30,400 does nothing. Okay. But if I send it to the same 30,400 with a name, it's in the header now, it sends to the correct service. So if I try to use HTTP, this works, right? And if I have some other service, I'll just create one more service so that you can see that, oh, this works. So I don't have results yet. So I'll create a completely new service running some web application. I'll create a deployment and a service for running that. So I'm running an Nginx server, a web server actually. So I'm creating a deployment and a service for that. Okay. So in addition to Vote, now I have uh, a web server called as Nginx, right? Has its own service as well. And now I'm gonna create web.example.com or something like that, which will point to Nginx service on port 80. This is clustered IP, not even exposed with node port or anything else, right? So I create a rule like this is the sample code where I'm doing the similar thing, just that this time I say web.example.com, send it to Nginx. Earlier I had vote.example.com, sending it to vote application. So it's almost similar thing here. And so now that I have uh, vote as well as web, right? So it's should be also available here. I already have created a domain name, by the way, entry pointing to the same IP that I've shown earlier. I'll just show you the configuration here. So in addition to vote, now it has web.example.com, which is pointing to a service. And this is one pod, but it's there, definitely there. So now if I send the traffic with this name, let me show you the entries. So I already had vote.example.com and web.example.com pointing to the same IP. So all of this is going to the same IP. Remember that. All of this is translating the same IP, but if I send it as vote.example.com, it goes to the vote application. If I send it as web.example.com, it goes to this application instead, right? That's the Nginx web server. That is how the ingress works. So what you see here is the ingress routing in action. Just like this routing, we have vote.example.com, we have web.example.com. And both are acting as routers. This is an application load balancer. So it is, picking up the endpoints on its own, doing the load balancing on its own. It is not involving service for the actual communication and load balancing. It just uses service to get the endpoints. So you see, if you describe the ingress, you're going to see it uses service to get the list of endpoints. And when the endpoints change, instead of 3 endpoints here, now we have 5, 3 plus 2, right? And that is where it makes a difference actually, right? So that's how it picks up the endpoints. And that is how it is able to route to this actual set of pods, right? That's how the ingress controllers work. Okay. Uh, any questions so far? Yeah. Okay. If you're on Zoom, you can also unmute and speak. You can chat, put the question in the chat. And if you're on YouTube stream, you can put this in the chat. Right. So about traffic and load balancing, you can influence the load balancing that traffic uses. So here it says the default load balancer of service type and so on. You can change the load balancing algorithms. There are something called as annotations. You can update the annotations to change the behavior of traffic and add further configurations to that. So there are a lot of annotations can come into play. And the way you communicate is via those annotations. For example, there is one annotation that we already have, which is used for some path prefix strip, right? So right now, if I try, I have this domain name as well, okay? There's an ingress and there is this kubefs view.example.com. However, if I send it to that, it just shows blank because it basically needs some additional configuration like this basically path prefix strip or something like that. And if I add it and let me try changing it and see if it is that one or something else, I'm not completely sure, but I'll try to edit the ingress whose name is kubeops view. Okay, and there are many annotations like this. So you can add more properties. We'll talk about one more annotation in deployment next session. And just gonna add one property here and check if this makes any difference. In case of kubeops view, uh, does not seem to be. There may be some additional configurations. I have to figure this out. But you can update the properties of traffic for a particular rule. You can add maybe a different type of a load balancing algorithm. You can add some TLS configuration. You can do that with annotations. Annotations are properties which are supported by a particular ingress controller. For example, traffic supports these kind of properties. So if you want to change the behavior of traffic and any configurations, you can do that from here. Let's say you add a TLS certificate. You can add what kind of load balancer is it, native load balancer or not. Do you want to use any other properties? You can do that. What kind of ports you have, you can define anything that traffic supports through those annotations. So your ingress rule will have the annotations. For example, you can also add default backend and so on. So in case of default backend, even if you send it with the IP address, it should send somewhere to that default backend and so on. So you can define these kind of things as well with the ingress configurations, right? That's possible. Okay, so Ingress is a useful thing, and that's how you typically expose your applications to the outside world. So, understanding the configuration of Ingress, how does it work, and understanding how Ingress controller would consume the Ingress rule. That is what I explained here, this diagram, where Ingress controller watches for the Ingress rules, and then whenever you make some changes, it will automatically update the configuration for its underlying application. That's how the ingress controllers work, and it's very interesting how all of this kind of pans out, right? So I've shared the labs for service networking. I've shared the labs for the ingress controller as well. Are there any questions that you have? All right. So what we're going to do is next week we're going to take a bit of a break because I'm also traveling, and we have combined, and from next iteration of it onwards, anyways, Ingress and network can go together because it's quite manageable to take these topics and combine them, and they're quite related to each other because we talk about service, and then of course the way to expose it is via, let's say, ingress controllers as well. So if you look at this diagram where we talk about services, so one of the ways is ingress controllers anyways, right? So we talk about all of this together, and that's what we will do as part of this mission as well. Even in case of the CKD topics, this is quite goes together too, right? So that's what we'll do, and I'm going to give you some buffer time if you are our members, and if you're following this pace of that hackathon or boot camp that we do. I'm going to give you some buffer time for next week, and you will work on these projects exclusively, complete everything till here, and then we come back a week after that and start with deployment, and then go on towards persistent data security and production, infrastructure and administration. Those are the next set of, and Ergo is kind of interesting topic, but it is not related to the exam or anything. So that's more like an educational, useful topic to learn about as well, right? But these are the ones which are also quite useful from the point of view of preparing for the exams like CKA and CKAD too. All right. So this mind map available there as part of our membership portal. So it will be part of that.
Hardly hear you, actually. There's a mic issue.
All right. Are you able to hear me now?
Yeah, fine.
Okay. Okay. I think I need to reset my mic. So this happens a few times. Sorry about that. Okay. All right. Are there any questions apart from this? So what I was just talking about is next week we'll not have a session, and I'll give you time to complete the projects. We'll have the Thursday evenings, Thursday sessions though next week. So I'll help you with the projects and anything pending from that. We can take up those, and week after that. So 1 week after next week. So next session is gonna be on. Let me just look up the calendar. Yeah, so the session planned for 6th of Feb will not be there. We will be back on 13th of Feb. So, and start with this on Feb 13. That would be our next class. And we'll continue with these missions from then onward. So for the members, you continue working on the projects. I'm gonna add the exams and projects till here this week, so that you should be able to complete work on this, and you get some buffer time there, right? If you are not a member, definitely consider being one. You get access to the relevant courses, projects. There are 20, 30 plus projects actually will be there for sure. And you get access to everything else as well, plus the weekly live calls for, and that could be useful too, right? So uh, definitely consider being one if you are not, and you can use the deal that has been shared with you on the YouTube live, and that would be applicable only for the first 10 enrollments. So you may want to consider that as well. So with that, we will, okay, are there any final questions? I think, okay, so there's a question from Chana Reddy. What is the app that you have used to design the roadmap with this? If you're talking about this is basically just my Word application or equivalent of that on Mac. If you're talking about this, I use something called as a mind node. This is the mind mapping tool, and this is always useful to organize your thoughts. So the way our brain thinks, you can put it on there. and that's this mind map. Mind maps are always useful, even for taking notes or just brainstorming, understanding a concept. That's the tool. Okay, so there's another question. If service discovery handled by core DNS, why kubeproxy is needed to enter IP table chain? Yes, core DNS is just a DNS server. The job of the core DNS is to store like a table of entries, domain versus IP tables or domain mapping to IP tables. And when somebody asks a question, answer to that. That's all the DNS server does. It doesn't actually update the IP table. It has nothing to do with IP tables. So you still need core kubeproxy to do that. So kubeproxy is still needed to update IP table rules, maybe IPVS rules in future. So it has a role to play there. All right. So the link for the Geek membership is already shared on the YouTube live session that you are. I believe it is. If not, just give me one quick moment, okay? Let me do that for you. Okay, so I'm gonna put this in the chat. Okay, this is with the code that there's a offer applied already, and you're getting basically the lifetime membership for about 50% off. And this is only for the 10 first 10 enrollment. So, whoever gets that first, you get that offer basically. Mind map file, I'll try to post it somewhere. I'll have to export it, upload it, share it. So during the next session, I'll probably do it. If you just want to take a screenshot, you could do that. So you just take a screenshot of this, or you will have access to the recording. From the recording, just take a screenshot, because even if I export it, you are going to see it as this. So, right. So you're going to see as just one PDF file like this. So you can just take a snapshot of this if you want to, right? And that is basically these goals. Probably that's what you're looking forward to. And it's also part of this document, which was shared earlier. I'm not sure where it is right now, but I'll probably put it in one of the videos or this video's description somewhere so that you have access to that curriculum. All right. So with that, we will wrap up this session. So thank you very much for attending today's session on Kubernetes networking. And we will come back and take up the next topic about deployment a week after this. So thank you and all the best.